Okay, let's solve this problem. How much energy does a human use in one day in kilowatt hours? And here, the question, although it doesn't state it exactly in the slide, we're going to do it for a human body. So not the total energy use that you're using with all your lights and PlayStations and things like that, but just the human body. How much energy used by a human body in one day in units of kilowatt hours? Well, we have to know how much energy a human body uses in one day in some sort of units. So we're going to start that off with um, this sort of recommended daily allowance of 2,000 calories with a capital C per day. So that's, certainly enough to keep a person alive. Some of us use more, some of us use less, depending on your lifestyle. And if you're a large person or a small person, we're just going to take 2,000 calories per day. So this is power. That is an energy divided by a time. So energy equals power times time. And my question is energy in one day. So the unit of time that I need to be working with here is power times one day. Energy in one day is the power that the human body consumes in a day, and the rate that it consumes energy in a day times one day. So I'm being super slow and pedantic here, I recognize, because you're going to see that this is going to look very silly in a second. So the energy in one day is the power, which is 2,000 calories per day, times one day. And the days cancel, and I just get 2,000 calories. Well, I could have just started off with that right at the beginning. That's sort of part of the statement of the question, but just to give you a little illustration about how these things interplay between power and energy. So now I just need to convert calories to kilowatt hours. So you could Google it. Just type in Google, convert 2,000 calories to kilowatt hours. We're going to show you how Google does it. Uh, so to do a units conversion, we multiply by a unit conversion factor where I have the thing on top and the bottom of the fraction here must be the same amount of thing, but just expressed in different units. So I don't know right off the top, or I'm going to pretend I don't know how many calories are in a kilowatt hour, but I do know that 4,184 joules is equal to 1 calorie. So I'm going to put 4,184 joules here and 1 calorie in the denominator. And I always start any type of unit conversion with an equation like this that I've just boxed in that is just saying one quantity in one unit is equal to a different numerical quantity in a different unit. That's my relationship between these two units. 1 calorie equals 4,184 joules. Then in my unit conversion factor, I put one of those sides of the equation on the numerator and the other in the denominator. And which one I put there depends on which one I want to get cancel out. I want calories to cancel. And this then gives me the energy that I'm looking for, not in kilowatt hours, but in joules. So 2,000 times 4,184 is 8,368 with 3 more zeros, so 8.368 times 10 to the 6 joules. That's 2,000 times 4,184, unless I made a silly math error in my head. So now I've got the energy 9 kilowatt hours, but in joules, and I remember that a joule is a watt times a second. So let's just rewrite it that way. That's 8.368 times 10 to the 6. A joule is a watt per second. And now I've got watts and time, which is going to make it easier for me to convert things to kilowatt hours. So let's put a unit conversion and just change that watts to kilowatts. I'm sorry, I wrote watts times seconds. Fortunately, I can digitally erase that. A joule is a watt times a second, not a watt divided by a second. Sorry about that. Watts times seconds. So let's convert the watts part to kilowatts. 1 kilowatt is 1,000 watts. I want to cancel out my watts and get left with kilowatts. So 1 kilowatt equals 1,000 watts. My watts cancel, and this gives me that the energy is 8.368 times 10 to the 6 kilowatt seconds divided by 1,000, which is 8.368 times 10 to the 3 kilowatt seconds. 10 to the 6 divided by 1,000 is 10 to the 3. Well, now I'm getting super close to my answer. Times 10 to the 3 kilowatt seconds. I want to convert the seconds to hours. That means I'm going to need some number of seconds here and some number of hours here. Well, 1 hour is 60 minutes, and a minute is 60 seconds. 60 times 60 is 3,600. So 1 hour is 3,600 seconds. My seconds cancel. I've got now kilowatts and hours left over as my units. I just need to take this number and divide it by 3,600, and the energy of a person that a human body uses in a day is 8.368 times 10 to the 3 divided by 3,600 kilowatt hours. And let's see what that number equals. I don't know if I was recording all that time, but the answer is 2.32 kilowatt hours. So what have we done? We've taken a long time to very methodically, painstakingly, slowly go through the conversion of 2,000 calories to kilowatt hours. 2,000 calories is about 2.3 kilowatt hours. That means 1,000 calories is about a kilowatt hour. And the second part of the example question says, how much would this energy cost you if instead of buying it as food, you bought it as electricity? So I don't know for how much you spend on food in a day, but it's many dollars, and depending on what you're eating and where you're eating it, could be tens of dollars for your food intake for a day. But 1 kilowatt hour of electricity costs on the utility market about 13 cents. So 2.3 kilowatt hours costs you about the energy cost in electricity equivalent of a human body for one day is about 2.3 times 13 cents is about 30 cents. Not very much. That shows us a couple of things, but most importantly, it shows us how incredibly cheap our electricity is. It's very, very cheap. It is what has driven so many of the advancements that we take for granted in our civilization right now is incredibly cheap electricity. And the reason it's incredibly cheap is that we're tapping into these abundant reserves of energy that are available, and we've developed technologies that can convert them to electricity very quickly.